If you're lapping the valve for anything other than to see what the seat looks like, if you're trying to save a cylinder head by using lapping compound on it in a performance environment, you're doing it wrong. Don't do that. If you're doing it to the point where you're worried about material removal or deformation of the valve or the seat itself, you're way beyond what you should be doing with lapping compound.
Welcome to the HPA Tune-In podcast. I'm Andre, your host, and in this episode, we're chatting with Tyler Hassing from Force Engineering. And Tyler is a little bit unique in that he is a one-stop shop / one-man band covering just about anything performance related. In particular, his background and training is in engine machining. So he runs his own engine machine shop, as well as, of course, building performance engines. On top of this, he's got his own chassis dyno. He does his own tuning. He even does his own fabrication. And Tyler's had quite a lot of success, particularly in the 4G63 world, which is my own personal passion. So we're going to dive deep into 4G63 aspects in this chat. But he's also currently got the world record for the fastest Gen 1 Ford Coyote with a stock block, that is, just to be clear, running 8.5s on the quarter. Now, it's not too often we get to sit down with an engine machinist that also has a performance engine focus, and there's a lot of really great detail in this conversation about the elements that go into machining a performance engine. Now, even if you're an enthusiast and you're wanting to build your own engines, I know that it's unlikely that you're going to do your own machining. I certainly don't. The amount of equipment required and the knowledge that you need to operate that equipment correctly is just beyond the home enthusiast. But there's some really great information that Tyler provides us here on some of the elements that we need to understand. Particularly, we talk deeply about ring seal and how that's going to affect the performance of the engine. We also talk about the differences between the modern CNC machining equipment that a lot of shops are now embracing compared to the older manually operated equipment and the pros and cons. Now, of course, CNC machine equipment does take a lot of the skill of the operator away from the end result. Now, of course, you still need to know how to use the equipment, but suffice to say, it's a little bit more difficult to get an accurate parallel bore with a manually operated hone compared to a CNC version. But we do see quality results being turned out by machine shops like Tyler's with this older equipment. So really interested to dive deep into that. As part of this, we also talk in depth about Tyler's world record holding Ford Coyote, the tuning options in particular that he has had available, because these late model cars like the Coyote, Mustang I should say, really they're one of those platforms where it has been difficult to remove that factory engine control module and replace it with an aftermarket standalone. So Tyler's gone from running the factory engine control module with a reflash to now replacing the factory transmission and going to a Haltech Elite 2500. So we talk about the pros and cons there. Some really great content in this chat, and I found it really interesting. I know you will too. Now, before we get into our interview though, just an introduction for those who maybe aren't aware of who High Performance Academy is. We are an online training school, and we specialize in teaching a range of topics in the performance automotive industry. Specifically, we cover performance engine building. We also cover engine tuning. We cover engine wiring, as well as race car setup, race driver education, and even some topics covering fabrication in the motorsport region. Now, particularly relevant to today's topic, we've got two of our courses that I thought you may be interested in if you like today's chat. Specifically, that is our Engine Building Fundamentals course and our Practical Engine Building course. These will teach you everything you need to know if you're a home enthusiast looking to take on your own engine building in-house. Particularly, you'll learn here about the inner workings of your engine, what you need to consider when building a performance engine. You'll learn about the tolerances involved, the clearances. You'll also learn what engine machining processes are involved, so you're going to be able to speak the same lingo as your engine machinist. And then in our Practical Engine Building course, we provide you with a simple 10-step process that you can apply irrespective of the type of engine you're building. Maybe it's a 4-cylinder twin cam engine, maybe it's a quad cam V12 or a pushrod V8, anywhere in between, it does not matter. This 10-step process breaks down what can seem at the start like a daunting process into something that's really easily manageable with bite-sized steps that you can go through relatively easily. In our practical engine building course, we also include a library of worked examples where you can watch that 10-step process being applied from start to finish on a real engine building job. We'll put the link for both of those courses in the show notes if you want to check those out. And as an added bonus, seeing as you are a podcast listener, you can use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. Again, we'll put the coupon code there in the description as well. All right, enough of an introduction for today's interview though. Let's get into it now. All right, welcome to the podcast. Tyler, thanks for joining us today. And I wanted to get started by just getting a sense of your background. I already know you've got a fairly wide talent array, including fabrication, tuning, and engine machining, as well as engine building. That's pretty rare in my experience. So can we dig in a little bit to how you got all of that knowledge?
Yeah, so I took over from my dad's when I was young. He's run this business since I was born, right? So when I was like 14, I actually took a class in school where I was able to work for him part-time, and then my mom drove me back and forth to school. But so we started doing the machine work stuff then. That's what he was teaching me back in the day. So he was just an engine assembly shop, and then eventually he bought an engine dyno. Actually had an engine dyno given to us by a friend, and that all carbureted circle track stuff or bracket race stuff back in the day. And I stumbled into the Turbo 2300 Ford world and I kind of had to learn how to tune the ECU stuff. So I had already known how to do the engine, most of the engine stuff, and then taught myself how to do the tuning. And the fab work was really kind of self-taught. I TIG weld a bit, and a lot of that stuff's just like learned by failure for me for the most part, but just trial and error stuff at the fab work. But we've come a long way now. So
I hope the trial and error wasn't on anything too mission critical, like an upright or a suspension arm.
No,
could end badly.
No, most of the fab work we did a lot of circle track racing, so we built some chassis components and stuff, but for the most part on my personal side of stuff I remember acetylene welding a header together in my parents' garage using a metal coat hanger as filler rod when I was like 15, so come a long way to the TIG weld stainless stuff that we do now. But
I think the oxyacetylene welding's almost becoming perhaps a lost art now with the abundance of high quality, relatively well priced TIG welders that are available. Let's just circle back to the engine machining. So you're obviously being sort of guided by your dad as you're growing up, getting into this at 14. I assume that's the case. Was there any sort of formal qualifications that you took as well, or was it literally just everything was passed on, all that knowledge was passed on from your father?
Yeah, it was all passed on from my dad. But yeah, I never did any kind of proper training or any education outside of what I learned from him on the machine work side of stuff.
Sure. In terms of the tuning, you said you're self-taught there. I hear a wide variety of stories on how that sort of went. So how did you learn those skills? Was it sort of a case of learning from failures or learning from others? Or how did it all work out for you?
Kind of a little bit of everything. So this would have been like 2003, 2004. Back then I had a Turbo 2300 Ford Thunderbird, which was a Van Air meter car. I don't know if you're familiar with, it's like a flapper door version of a mass air sensor. And I was tuning that with, I would take the Van Air meter apart and adjust the spring tension on it, and then had fuel pressure I could move up and down. And basically I couldn't afford a wideband, so I'd tune by reading plugs. And then just would move the distributor for total timing adjustments and use the factory timing curve.
I think it's important to understand that people these days who are just starting to get into EFI don't realize how spoilt they are with the options available and the precision with which you can make really specific tuning changes just at one load and RPM point. But much like you, I've been through that right as well. And this is a story I told a few podcasts ago, but back in the early days, adding a turbocharger to a Honda B18C, I think from memory it was, and adding an auxiliary injector to keep up with the fueling when it was into boost, and then retarding the overall base timing in order to basically prevent the thing from knocking. It's not elegant, and I wouldn't do it today, but there's ways around this. The trapdoor airflow meter as well. Absolutely horrible thing. Every car I ever tuned with one of those, you take that out, and straight away, if you could tune without that on an aftermarket ECU, just getting rid of that horrible restriction was probably worth another 20, 30 horsepower. They're a terrible design.
Yeah, it was significant. They were bad. I remember the software I used back then was called PCMX to use the factory Ford ECUs. You had to have a chip burner, and you couldn't really data log. So I had a voltmeter. I ended up putting a lightning mass air meter on it, and then I would data log with a voltmeter. And I would basically have to watch the voltmeter to see where in the MAF table it was to make the changes, and then read the plug, and on it went, right? So yeah, it was time consuming.
Suffice to say that life is a lot easier for us these days. However, further into this conversation, we'll get into some of the pros and cons of the more modern Ford ECUs and how they make our life a little bit more difficult in some ways when it comes to tuning them. Now, getting back to the engine machining, because I sort of want to focus a little bit on this. I'm going to be a little bit selfish here, and there's some information that I really want to drag out of you, particularly because we share a common passion with the Mitsubishi 4G63. And engine machining is something I have never delved into myself, not just because I wasn't privileged enough to sort of grow up with a father that could teach me that, but if you don't inherit a fully fledged engine machine shop, the equipment required and the outlay that's just obviously prohibitive for the average enthusiast. So I've left that to professionals, but I've got a sort of a cursory knowledge around the edges of that. And one of the things with all of the machine shops that I have used over the years, both here and overseas, is I see a massive variation in the age and quality of the equipment in the shop. And while on face value you walk into a shop that has brand new CNC equipment that looks like it's probably a good thing, what I want to get a sense from you is how important is the quality of the equipment versus the skill of the operator?
I feel like there's a trade-off there as far as talking specifically about quality and not the quantity of turnaround, right? Obviously, the modern equipment allows you to do things much quicker once they're set up correctly. There's a few things like I have a Rottler 85B decking machine. Now it's a 16 insert cutter that turns at a rather slow RPM, and getting the deck surface down to like under a 50 RA was a challenge for a long time. That was difficult to do, and a modern piece of equipment could do that very easily. So in that instance, I would say the equipment's pretty crucial. In the majority of stuff that I do, though, like cylinder wall finish on my old CK10 with like a manual dwell control, so I can control how long it sits at the top and bottom of each cylinder for sizing. To a modern one that would basically automate it and do that by itself, the end result's going to be the same. Again, it's just going to take me a little bit longer to get there than a modern piece of equipment.
So again, not that I've been involved in this aspect of the engine building process, but from what I understand, particularly when it comes to honing the bore, you're talking about the dwell there, the position of the hone in the bore and how long it's in a certain place. It's very easy to introduce sort of not out of round, I should say, belling or a taper in the bore. So is that the sort of aspect that comes down to the CNC will automate that, so you can pretty much guarantee you're getting a nice parallel bore from top to bottom, whereas with a manual machine, a little bit more skill in the operator to make sure you're not introducing that?
Yeah, correct. You have to pay, like, one of the things you have to pay really close attention to is the temperature of the material when you're honing it too, because the block can heat up in different areas. Obviously, in the middle of the cylinder, there's not as much material behind the cylinder to pull the heat out of it. So it's often that just from the actual honing process, even flooding that thing with coolant, that it's really easy to get the middle to be big when you're honing it. And then when it cools off, like you said, it's bell-shaped. The middle will be small. So you got to pay really close attention to that, whereas a CNC, I think, does a better job of compensating for it. I haven't used one, so I don't 100% know, but they definitely do a better job of controlling the stroke and the dwell. You can see they'll have a display up on the computer when the CNC hones are running that shows you what size the cylinder is and when and where and how it's adjusting for it. And really cool stuff. Whereas on my end, I have to hone it for however many strokes. I usually count them in my head, and then I pull the hone out and I'll measure it by hand, see what stuff's looking like, and adjust it accordingly. And then, you do, like typically on a 4G, I'll do cylinder 1 first and then cylinder 3. So it's the furthest one away to try to keep them temperature-wise similar while I'm going through it.
So after that, do you then allow the block to cool for a period of time before you do 2 and 4?
Yeah, yep, generally, yes. And then also, like, as I'm honing the block, the block as a whole won't gain, like, externally. If you shoot a temp gun on the water jacket, it doesn't gain a lot of temperature. It'll gain, it's 69 degrees in the room. It'll usually be 85 or so by the time I'm, say, done with all of them. And at that point, I'll let them cool back down to 69 degrees and recheck everything at room temp, because that's where all their tolerances are based on, between 68 and 70 typically. So yeah, there's quite a process of stuff to pay attention to. Now, I would say that a lot of that stuff you would also have to focus on in the CNC world. Like, you can't just let the machine run and negate the temperature effects of the honing.
Yeah, I mean, it doesn't really matter if it's manual or CNC. It's an abrasive process which is going to add heat into the block, correct?
Right, yes.
Now, a lot of this really comes down to optimizing the ring seal that can have a really dramatic impact on the performance of the engine. And we've just talked there about the sort of ability to get nice parallel bores and get rid of the potential for belling or taper top to bottom. And that's going to allow the ring to potentially do a better job of sealing. Likewise, we ideally want a bore that is perfectly round. And while most cursory glance you would expect that your bore is going to be perfectly round, particularly when you start bolting the cylinder head onto the block, the distortion that occurs can be quite significant, correct?
Yeah, I know 4G specifically. Now, I do had arguments with people about this, but when I do a torque plate hone, I use like an MLS head gasket. Particularly, I'll use whatever head gasket the customer is planning to use in the end, so I know that the distortion of the cylinder is best simulated as I can, as close to when it's assembled. But yeah, depending on like a HKS MLS for the 4G, it'll move. I think the top of the cylinder will close like 9/10 to 1.2 thou, and the top only like inch or so of the cylinder wall. And then down it can kind of put like almost an S shape into it on some of the blocks, not necessarily always on the 4G, but like the early 2, 3 Fords, the cylinder walls and those things are super, super thin. But the bolt point where the cylinder head threads are is at the very top of the deck, so it distorts the cylinder much differently, which is why it's so important to use the torque plate on every engine you're honing, right?
Sure. So you're talking there about a distortion, did you say 1.2 thou?
Yeah. Yeah, it's significant.
You might be running a piston to cylinder wall clearance of maybe 4 to 5 thou or something of that nature, just to put some numbers around that. So that is clearly a significant difference, even though we are talking about very small measurements, correct?
Correct, but the biggest difference is at the very top of the bore, and it's actually like above. It's so high in the bore that it's above the max diameter of the piston anyway, right? So like, how the piston's got a bunch of taper built into it. So that's how people get away with honing stuff with no torque plate, is the part of the block that it actually distorts is so far above where the skirt is actually contacting the cylinder wall that the effects can be a little negated. Now, that said, it is going to affect like your ring end gap. So you got to leave some room in there if you're honing it without a torque plate for sure. But
I mean, ultimately, the upshot of all of this is, even if it's minor, this is going to have an impact on that ring seal and hence the potential amount of power that an engine's going to make, all other things being equal.
Correct. Yeah, no doubt.
Okay, now another technique, I don't know if you've had any experience with this. It's something that a machine shop I have used a couple of occasions have. They do a lot of high-end race engines that are for controlled classes, where obviously everyone is sort of trying desperately to get every last horsepower out of a very tightly controlled engine. And the the hardware that they use is called a hot hone. So again, from what I sort of gather here, we're just trying as best we can to replicate the actual operating conditions of the engine so that the bores are as perfectly round and true as they can be under those conditions. So we've talked about the torque plate there and the distortion that creates, but of course we can also end up with the bores moving around a little bit when the engine's at an operating temperature of maybe 80 to 90 degrees C. What's that, maybe 180, 190 F. So I'm not sure if you've ever dealt with that, but do you know anything much about that and what the usefulness of it is?
Yeah, so like you said, they're trying to duplicate as close as they can as what the engine running conditions are, right? So they're getting the engine up to close to operating temperature to make sure the cylinder wall distortion is still straight when it's up to temp. There's a couple arguments, not necessarily that I have against that, but that I would say that doing a hot hone might not be worth the extra effort. One is you then have to know what you want your piston to wall to be at 180 degrees and not where the manufacturer's spec is at 70 degrees. The other thing, too, is trying to get the cylinder distortion out of it is important, but the cylinder is going to distort a lot when it's got 3,500, 4,000 pounds of pressure in it. So I think that we can do the best that we can. I don't know if going to the extra effort of hot honing is worth a ton. I'd be really curious to see with like a crankcase pressure sensor on a same ring pack, same for same, if it made a ceiling difference at something that was making a moderate power level where you had, 3,500 or 4,000 pounds of cylinder pressure, how much distortion is still happening just from the sheer force in the bore.
That's a really good point. I think it's easy to overlook what's actually happening to that bore in operation, as you say, with such massive cylinder pressures as well. Again, not a technique that I've personally had experience with, but just something that I was interested to learn about there. Now, moving on with the actual process, and I just sort of want to talk through maybe some of the steps involved with typically machining a block from start to finish. Again, a lot of what I want to talk about here will be applicable to just about any engine, but some of this I'm going to dive in specifically on the 4G because I know that's a platform you've got a lot of experience with. And we obviously want to start with cleaning all of the componentry down, and particularly if you've got a high mileage engine, there's going to be potentially a lot of gunk and sort of oil sludge built up and baked onto the inside of the block. And we sort of hear the different options of cleaning, including hot tank or vapor blasting or even sandblasting. Can you sort of give us your take on what the options are and what is most suitable, what's going to get us the best result?
Yeah, so the two options that I use, I don't do it in-house, I outsource it to somebody, but they call it a bake and blast process, where it's basically like in an oven and then it's a steel shot that they shoot at the block. They come back looking like brand new cast iron at that point. The advantage that I feel to that over like a vapor blast would be cool using a media that's water soluble, like baking soda, for example, right? But anybody that's like glass bead or any kind of abrasive that is difficult to get out, you're never going to get it out of everywhere. That's the biggest concern I have with that.
Yeah, I have had a fairly nasty experience back many years ago with exactly that scenario. I mean, if you're using a glass bead media, it does an amazing job of cleaning up, particularly an aluminium casting like a cylinder head. But exactly that. I mean, you can do your absolute utmost to clean everything, and there's just so many little sort of hidden areas inside a typical head casting that trying to clean that back out is an exercise in frustration, and doesn't really take much glass media to go through the engine when it's up and running, and it's going to end up causing some pretty nasty damage pretty quickly.
Yeah, for sure. We actually quit sandblasting cylinder or blast media, whatever, blasting cylinder heads at work because of that. Is what we found is if you got all the oil galleys and like in a 4G head, you've got oil to the lifters or the lash adjusters, whatever you want to call them, and all the other stuff. There's just a million places for the sand to go. You get all that stuff out, and it's still in the coolant passages. So you wrap that cylinder head in a baggie, and it ships across the country. It's getting shaken and tossed all around. You just can't never get all that stuff out of there. So definitely stay away from that if you can. Like I said, a vapor blast, I've been looking into that, actually doing something with baking soda, some sort of water-soluble media alleviates a lot of those issues.
So the advantage there with the media being water soluble is you can put it through your hot tank or give it a good clean afterwards or whatever, and that's going to basically dissolve any remaining media in the head, and you can actually guarantee you can properly wash that out.
Yeah, in theory, yes. I don't know how well it actually works in practice, but yeah, that would be the idea, right? I have a hot tank at work too. That's just it's just a caustic soap, just a normal hot tank thing, and that does a really good job with cylinder head stuff. It does a good job with the small. I can fit a 4G block in it. But back to the bake and blast for the block side of stuff, that stuff comes back looking like literally brand new cast iron. Whereas if you just stick it in the hot tank, it's cleaner, but it only does so much. So
I just actually, while I'm thinking about it, just the dangers of blasting media, I just wanted to recount. I just basically went through a bit of a nightmare while you were talking there, because this all came back, flooding back to me years and years ago. I built a 4G93 through my old business for a customer. So that's a Japanese domestic market model. Basically, it looked like a Mitsubishi Evo 1-3 shape, but it was the 1.8 litre twin cam engine. And at the time, we had a car that I think ended up setting the world record on the quarter. I can't actually remember. It was in the 9s, but that's really irrelevant. I built the motor for this customer, and he supplied me a rocker cover to go on it, cam cover, and he'd had it shaved and powder coated. And I didn't really think too much of it at the time. And we got the engine up and running, and basically during the running in process, it ran all of the bearings, which obviously for a freshly built engine is the worst case scenario. Yeah. Long story short, what we found was that during the powder coating process, the operator who had done that, he sandblasted the outside of the rocker cover, which is a pretty typical aspect of powder coating. But I was unaware of any of that, and basically we drilled through the little baffle plate on the inside of the rocker cover, and there would have been probably half a cup of sand came out of that. So we'd literally just been pumping sand through that. So that's just a trap to watch out for, because I know there are a lot of powder coaters, they don't really know anything about engines or the potential pitfalls. So that is something to really watch out for, because it can be a very expensive trap to fall into.
Yeah, I actually had a similar experience with a 4G valve cover, but also with that, if you notice, the intake manifold on my personal car currently has an air-to-water intercooler in it. Like, it has a Garrett core in the bottom of the plenum. And I sent that out to get powder coated, and I told him not to blast it. Well, he apparently just blasted it anyway. I spent, I don't know, days cleaning the sand out of that thing. And then you never know if you got it all. It was scary. I was nervous.
Yeah, that's never a good situation. I think that also comes down to a very similar scenario with engines that run an oil to water heat exchanger, and that's pretty common with a lot of engines, I find. And if there has been a bearing problem with those engines, or actually even with an external oil cooler for that matter, right, it's really easy to go and have your engine rebuilt and then put it back together, get it up and running, and have almost exactly the same failure just a few hundred miles down the track as a result of the oil cooler, be it an external one or that water to air that I mentioned, actually trapping particles of the bearing material, and then those get released and pumped through the engine. So I personally have never found a way that I would trust to clean those out, and I sort of just ended up adopting the process of replacing it with a brand new unit. For me, it was, particularly for a customer engine, it was peace of mind. I could guarantee the result. So that's something that I know a lot of people overlook when they have had an engine failure.
Oh, for sure. Even engine oil, but also external transmission coolers. If you have a trans failure, I've seen that bite people before too, where the material is just stuck in the cooler, and no matter what you do, you flush it out and do the best you can, and you think it's good, and then it's not. It's just, I'm with you. It's just best to replace it. Another thing that I see it have happened before is in like a car that's getting worked on with no charge pipes on a front mount intercooler, and the intercooler is sitting outside and there's no caps on it, and the core can get sand in it. Not many people think about that. They just throw the engine back on, charge pipes in it, and run it, and then we wonder why, they're having bearing issues, or the rings never quite seat because it's got, it's basically sanding everything off it. But
Yeah, those are all the little tricks that are so easy for people to overlook. I'm really fussy on that. We always cap any open plumbing when we're working on an engine, even if you're just fitting other parts and you've temporarily got an intercooler pipe removed. I mean, it only takes a few seconds to jam a rag in the end of that pipe so that something doesn't get dropped down in there. If nothing else, it's going to save you a bunch of time trying to recover a nut or a bolt. They always go into the most awkward places. It's just about guaranteed. All right, let's move back on to our engine machining steps. So we've got the process of cleaning those parts down. The other one, well, the next one that I want to talk about is block preparation. This is something it looks like you and I probably share a bit of a similar philosophy on, but I mean, I know a lot of people really don't do anything with the bare block. They just go ahead and start assembling the components. So can you talk us through what steps of block preparation are required and what you go through?
Are you talking post-cleaning?
Yes, correct.
Okay, so depending on what the combination is, like example is aluminum rotted 4G. I'm going to mock that thing up multiple times and just check rod clearances against the bottom of the bores and all your typical stuff, the main caps and the 6-bolt. You got to cut those out of the way. Just confirm all that. And then I'm, typical stuff, right? You're putting main studs in it and a girdle, make sure the girdle doesn't hit anything, torque everything together, check all your main housing diameters, you check bearing clearance while you're in there, that kind of deal. Is that what you're asking?
Well, sort of, let's go back one step, and maybe this is a case of pre-cleaning, because I know it's going to create a hell of a lot of mess. But I know a lot of the cast iron blocks, and this definitely goes for the 4G63, we end up seeing a lot of casting flash inside of the block. I tend to remove that, and I've seen on your videos you do the same. So how critical do you think it is to go ahead and do that sort of work?
So I do that on like a case-by-case basis, right? Some of them are really, really bad, to the point to where you get in there and you start brushing stuff with your fingers and the casting flash is falling off as you're pushing it. Like, you have to remove that stuff. It's going to cost you an engine if you don't. So yeah, I'll go in there with a sand roller or a carbide burr and just pull all the casting flash off that I can reach. You can never really get into all the angles, it seems. And again, that's a case-by-case thing. Some of them have casting flash just at like the seams and that kind of deal, and it's not that big a deal. But some of them, it's bad. And not only is the flash a problem, but the casting flash itself holds material or debris or any like that in there. So as you're machining it and you're making dust with cast iron from the boring process, or you're grinding aluminum rod clearance in the bottom of the bore or whatever, that can get trapped in that casting flash and eventually work its way out. That's the biggest reason why I do that.
Yeah, no, I think that's a perfectly reasonable point. And as you mentioned, it is a case-by-case basis. Some blocks are actually pretty smooth internally and really don't need much work. But I have had exactly the same scenario where just a little bit of pressure with a steel pick or something of that nature can break off a section of casting flash. And on a few of our videos, we've had a few people comment, why are you bothering going to that trouble? That engine's just done, 50, 60, 100,000 miles previous and nothing's broken off, so obviously it's fine. Which I'd sort of counter with, well, yeah, obviously it has been fine up to this point, but when we build a performance engine where we may be looking to extend that power range by 20%, or maybe we're looking to double or even triple it, there's a lot more stress that's therefore going to be placed into the block. It's going to move around or flex a lot more, and that can therefore end up breaking some of that casting flash free, where it would have stayed put and been quite happy for the rest of the engine's life in stock form. Obviously begs the question, will it happen? Hey, who knows? But from my perspective, an hour or so on the end of a die grinder or a sanding roll or whatever you're using to remove that casting flash, for me that's good insurance, and particularly when you're doing this for a customer's engine. If it goes bad, you're the one that's sort of holding the can at the end of the day, correct?
Oh, yeah, for sure. And it doesn't matter what the failure was. They're going to come to you for, not necessarily blaming you for anything, but with questions anyway. You got to have a way to answer those. But yeah, it's definitely good security to go through and get the casting flash off when it's needed. And another thing, those people that are asking, like, well, it just slid 50K in a stock vehicle. Well, that's probably true at an average RPM of 2,500, not 9,500. You know what I mean? Like, totally different harmonics, like way different environment that can cause that stuff to fall off.
Yeah, absolutely. I think it's very easy to overlook that most regularly street-driven cars, the engines do not get a particularly hard time like they will in a modified or race application. All right, so moving on, you did mention the aluminium rods and clearance. Now, obviously, for those who haven't seen alloy rods, we don't have the benefit of photos on a podcast, but they're significantly more chunky than a steel rod. And that's natural because of the strength of the material. Even with a beefier rod with the alloy, you end up with a lighter rod overall, but that requires clearancing. And I've done this on a few occasions myself, and I find it a fiddly operation because you're sort of dummy assembling everything and you're trying to see that clearance between the beam of the rod and the underside of the bore where you can't easily get into. Have you got kind of any tips for us on how you go about knowing you've got sufficient clearance? And maybe for that matter, what sort of clearance you deem as a minimum in those areas?
Rule of thumb is 60 thou everywhere. I know I've ran it tighter than that, probably down to half of that, actually probably down to 30 without any issues. But as far as checking it goes, I use clay a lot. I'll just stick clay down in the relief I've cut for the connecting rod, roll the thing over so it leaves an impression, and then cut the clay in half with a razor blade or whatever, and then measure the thickness of it. But it's not a perfect process. It is difficult. Like you said, it's a lot of trial and error. Because that's just part of that game. You just got to clay it 3 or 4 times. With the 4G, I've done enough of them to where I can pretty much eyeball it, put some marks on it, and cut it out. It's not a big deal. But with another engine that I haven't done, it would be it's definitely time-consuming.
Yeah, it's not something you want to second guess and sort of hope that you have enough clearance. You definitely want to be confident that it's going to be okay in operation. Now, another aspect with just about any high-performance turbocharged build is head gasket sealing, and I've said this on the podcast a few times in the past, so forgive me for those who have listened to them all, and I sound like a broken record. But that was kind of the limiting factor when I was drag racing our own shop car. We were basically limited by how well we could hold the head on the block. And I experimented with a few options and basically ended up going down the path of an MLS gasket with a stainless O-ring in the block with a light protrusion. What have you found to work, and what are sort of the techniques that you'd recommend for different applications?
So using the 4G as an example, I do, typically I'll run an MLS up to say 600 pretty reliably. Between the 6 and say 1100 area, I do an MLS with a stainless O-ring in the block, low protrusion thing. With good luck, anything over that, I tend to do O-ring receiver groove, copper gasket stuff. Okay. There is some new stuff coming out with the Athena SE. Well, it's SE owns it. Was Athena. Are you familiar with those? Have you seen those yet?
Yeah, the cut rings. I've actually just installed one on an Evo 9 engine that we've built for one of our in-house projects, but I've had no trouble with that gasket at all so far, but that's mainly because the engine's still sitting on a stand. So we'll get to put that through its paces and see how it goes. But for those listening who haven't heard of that, can you just talk us through what that Athena gasket is?
Yeah, so it's a solid proprietary material ring in the center, and then it uses like a composite gasket. The rings are free floating, so you lay the composite piece on the head, and then you lay the rings in each individual cylinder. It's a solid ring. The STE version of it has 3 little teeth in the top of it that will dig into the cylinder head, and they're flat on the block side. And then obviously as you clamp the cylinder head, the composite material is going to give to a dimension, whatever STE deemed was correct for that, and then you're going to put a lot of press on the top of that material ring, that solid ring. That's going to be your seal. The downside that I see to those, as I'm looking at them as a replacement for doing an O-ring MLS combination, right? You don't have the additional machining of putting an O-ring in the block, and then when you want to, say, deck the block down the road, you don't have to dig those O-rings out. I don't know if you've had to do that, but that's not an easy task to do.
No, it's a pain in the ass, particularly if you've got the O-rings fitted nicely like they should be.
Yeah, correct. And then the downside I see to the SCE thing, though, is that whenever you remove the cylinder head, you're going to have to deck it because you got to pull the teeth are going to leave rings in there. But
yeah, correct.
I think it's a good alternative to that, though. I think it's a better end concept than the O-ring MLS steel. Now, that said, I've had really good luck with that, but
Yeah, we ran the O-ring MLS gasket, and for those who are interested, the gasket we used was the 1.2 millimeter HKS stopper type. So yeah, just an off the shelf, nothing particularly special about that, and that was good too. We were running 56 pound boost, which is obviously nothing by today's standards, but that was about 1160 wheel horsepower for our 4G63, which that was pretty good back in the day. Obviously, again, a lot of cars making more power than that now. Another option that I haven't personally played around with myself, but I know a lot of high boost turbocharged engines are using, is a step deck, which I'm guessing probably really is going to require a CNC to cut that, where there's sort of a section around the bores that's left a little bit high of the rest of the deck surface. Have you got any experience with that technique?
Yes and no. I do in sleeved aluminum blocks, right, where it's got an aftermarket sleeve. A lot of times the block will be out 5 to 10 thou from the deck surface. I believe the initial intention is that the sleeve is going to grow at a different rate than the block is, so at some point that distance is going to change. But that's the extent of my experience with that. It would make sense to do a step deck. The problem is if you have to repair it, if you damage it and you have to fix it, how do you do that?
Yeah, that's a good point. I mean, it really is sort of a one and done type of deal. I mean, you're really going to have to deck that whole surface back to flat if you're going to try and recover it and go again, and that's obviously going to end up removing a lot more material than you would necessarily need to do if you were just doing a light cut to clean it up, correct?
In theory, yeah. I mean, being that I don't have a lot of experience with it, I don't know for sure. But yeah, that would be my thought, is that repairing that's going to be, you're going to get a lot less opportunities to fix that specific block than you would a typical setup.
Yeah. Can we talk a little bit, I don't know if this is proprietary information that maybe you want to hold tight, which is absolutely fine, but maybe if you could share some information around the protrusion of the O-ring that you're using, and maybe how that differs with a relatively solid gasket like an MLS versus the O-ring with receiver groove that you run with a softer gasket that deforms like copper.
Yeah, so the MLS stuff, I'll run a 5 thou. 4 to 5 thou is my target protrusion on a stainless ring MLS gasket. With the copper O-ring receiver groove stuff, there's some proprietary stuff on the receiver groove depth that we've sorted out, but the actual O-ring protrusion itself, we're usually shooting for 15, and that works really well up to, like, say, a 60 thou gasket. Any more than that, we haven't had issues with it, but I tend to get a little bit timid about running that with a thicker gasket, just because the copper doesn't push into the receiver groove as much, so you don't get the nice sharp corners on the receiver groove side of it where it's actually holding the copper in place very well.
And it's that sort of tight square edge that's really locking that copper into the receiver groove and giving you that good seal that you need, correct?
Correct. Yeah. Yep.
Just in terms of the receiver groove technique, am I right in saying there you're putting the O-ring into the head and the receiver groove is going to the block versus how you do it for an MLS?
Correct. Yes. And the reason that we do that is if you put the receiver groove in the cylinder head in an aluminum head environment, if you do have a gasket failure, the sharp corners on the cylinder head will be rounded. It will not grab the gasket as well around the corners of the receiver groove that you've cut in it. And then you have to deck it and recut the groove to get the corners back. Whereas if you put the receiver groove on the block side, you lose the gasket. It rarely hurts the cast iron. So those corners stay nice and sharp.
All right, let's move on to the cylinder head, because another area that I think is probably a little unique with your skill set is that you're also involved with your own head porting. And I'll admit, just like the engine machining, this is an area that I've got some sort of cursory knowledge around, but I have purposely stayed away from it. I've kind of almost seen that head porting is one of those areas where science and art kind of merge, and I've also had experience in the past, and this actually came down specifically to some Honda B-Series engines where I had a run of them that I was tuning for customers, where the customers had spent quite significant amounts of money on head porting on those cylinder heads. And when we actually went and tuned them on the dyno, in some instances, they were no better or even in some areas worse than stock. So what I take away from that is head porting is something you need to deal with carefully, because it's not a case necessarily of big is better, and you do have the potential to go backwards if you don't know what you're doing or you get it wrong. So I guess the first question there is how did you dive into the world of head porting, and how did you learn?
So back to my dad, he's 72 now. I have 71 this year, I think. So he was doing cylinder head porting work back when you couldn't call Summit and get an aftermarket set of cylinder heads for a small block Chevy. So he was porting iron cylinder heads for any kind of factory small block that came through there. So that was just a big part of the process. He worked with a guy named Jerry Arnold, who was a NHRA comp eliminator champion couple times over, and he had a flow bench in his garage, and my dad and him would go work on the flow bench back and forth and would design ports that way. So that's really how I got involved with that, was just, again, knowledge passed on from my dad and from Jerry. The hard lessons I've learned with that are kind of twofold. The flow bench can be misleading. I've had in 2300 Ford stuff, when I was messing with that, I had a cylinder head on the flow bench that picked up I think 10 CFM, which it was flowing 200, so 5%, so significant. But it lost 18 horsepower on something that was making 460, I think, at the time, which I thought was really interesting. I think that there's a lot more going on that the flow bench doesn't show us. That's why wet flow benches are a thing. You have guys with benches that are measure tumble. They'll measure rotational airspeed, the torque of that airspeed, all kinds of stuff in the cylinder. I think you have to have, I'm going to go off track, but I think you have to have a good feel for what you're doing on a flow bench and how what you see on a flow bench relates to what you're going to see on an engine dyno. You have to have a relationship there that you're comfortable with.
I'm glad that you brought that up, because I think it's almost like engine dyno numbers where people think bigger is better. So, a port job that shows that it picked up, 10 or 20 or 30 CFM, you think on face value that sounds great, but really what matters is what's happening on the dyno. So there is that relationship there. And from, again, not being personally involved in this, what I understand is that it's not just the air flow that's critical here, it's actually also the air velocity. And you can go and improve the airflow, but destroy air velocity, which can end up being really detrimental to low RPM torque. So if you've got access to a flow bench, is that in itself only a tool that is useful when used in conjunction with an engine dyno to actually validate the results you're seeing on the flow bench?
In my opinion, I would say yes. Now, the reason that is my opinion, though, is because I don't have enough hands-on experience on a flow bench. A lot of guys that'll use a flow bench in and out all day, every day, will know how the bench is going to affect the dyno just from trial and error. And because I don't have that knowledge base, I would have to have both. I would have to do something on a flow bench and then put it on the dyno, where, as in what I'm doing now, I just have the dyno. I just skip the flow bench process altogether, which is a skill set that I wish I had at times. I'm sure there's times it would benefit me having that knowledge on how one correlates to the other, but I don't have it. And I don't have the opportunity to really have it. I have to buy a bench and spend hours and hours of time going from bench to dyno to bench to dyno, so.
Yeah, unfortunately as well, and unless you're working with a fairly high budget for a race program, that sort of work is often, for the majority of us, just simply financially unrealistic. The time consuming aspect of it and the back-to-back comparisons, it's just not something that unfortunately we can do. So, well, a lot of us can do. So that's sort of worth just understanding there. Just bring this back to the 4G63 world again, and there's a big difference between the cylinder heads for the earlier 6-bolt 4Gs and the later 7-bolt. Particularly if you look at the intake port, those 6-bolt cylinder heads were an absolutely massive port, although they did use an inlet manifold that sort of had butterfly valves to block part of that off for low RPM performance. But looking again at that sort of is bigger, better, what's your sort of experience been on dynoing the big port versus the small port heads?
Well, I would have 2 points to make with that. The opening size is, yes, very different. The actual minimal cross-sectional area of the cylinder head isn't as drastically different. I used to know those numbers off the top of my head, and I don't anymore. But I've had both of those cylinder heads. We've made great horsepower with them. I mean, good example of a set of heads I do, or a 4G head that I do, is for Aaron Gregory. That's a 6-bolt cylinder head. That car's been, I think, 709 at 199 kind of deal. And then Kigley's car, Kevin Kwiatkowski's car, yeah, that's a 7-bolt cylinder head that he's done himself, and he does all the cross-sectional area modifications to it to get it a little bit bigger than the factory 6-bolt cross-section. So yeah, I think that what I do like about the 7-bolt head over the 6-bolt head is actually what it allows you to do on the intake manifold side of stuff. Because the 6-bolt head is so big at the flange already, it doesn't give you a lot of opportunity to build a nice taper in the runner. Whereas on the 7-bolt head, you can have a more tunable runner configuration, in my opinion. But again, I mean, I don't even know how much power Aaron's car is making, but it's got to be 2,000 horsepower at the flywheel out of a 4G, I would imagine, to go 199 mile an hour in a 2,600 pound car. So,
yeah, it's got to be there or thereabouts, surely.
Yeah.
So it's not lacking, put it that way.
Correct. Yeah. And that said, Kevin's car, he's been 191 on a 7-bolt head. So yeah, I think they're both okay. I feel like, again, the intake manifold options is a crucial point there.
Now, while getting that last sort of percentage out of a cylinder head might involve either the flow bench or flow bench plus dyno, and probably almost certainly a head porter with some fairly extensive experience on that platform. From my take, there are some sort of low-hanging fruit, if you like, with head porting that you could apply to most cylinder heads around aspects like the short radius, cleaning up, casting flash, maybe kind of cleaning up any core shift as well. So can you talk about some of those aspects? Is that sort of the area where you can maybe get sort of 60 to 75% of the potential gains that are available?
Yeah, for sure. My rule of thumb is always an inch either side of the valve is the most important area of the cylinder head. Anything outside of that isn't as crucial. That's where, like you said, the last 10% is going to come from manipulating the runner, but the bulk of it, the real meat of it's right near the valve area, right? So the valve job is very crucial. Then, like you said, the short side radius, making sure that that's just shaped how you want it, and how you want it's going to depend on the cylinder head you're starting with, where the valve placement is, the angle of the valve in correlation to the cylinder, all that kind of stuff, right? It's going to be crucial how you want that short side radius shaped.
With that short side radius, and again, we don't have pictures, but it's probably pretty self-explanatory from the term. It is that tight radius on the inside coming down to the valve. Is that, I hear that this is the critical element with head porting time and time again, and is it about trying to get that airflow to stay connected to the port wall, essentially, as opposed to separating and causing turbulence? Is that the sort of aim there, or is there something a bit deeper going on?
Well, there's a lot going on. Yes, trying to avoid turbulence is huge. Anytime you get a turbulent port, it becomes a mess. I don't know if I would necessarily say wanting it to get to the stick to the port wall is what you want. You're just trying to move the air around the valve as most efficiently as possible, right? The other thing that is something to keep in mind too is fuel atomization. If you get like some of the air gets turbulent, the fuel can fall out, and then you have atomization problems. So you got to be careful there. Now, that's not as crucial around the short side radius. That's more in the valve job specifically. But it's just something to keep in mind. I feel like the short side, the shape of the short side is all about just getting the air to move around the valve. I mean, that's the whole idea of the port. But as far as getting it to actually stick to the wall, I don't think that's really your main goal there. I don't.
Yeah, no, fair enough.
Yeah.
All right, I did interrupt you there, so let's get back to those other elements. I mentioned core shift in there as well, so can you sort of clarify what that is and what you're trying to correct?
Yeah, so core shift, good examples of 4G head. If you were to like take one upside down and look at it and look at the the distance from the center of a valve to where the edge of the chamber is in relation in the factory machine, how much material that factory machining process removed from one chamber. Say if you look at cylinder 1 and cylinder 4, they're typically always inward on each other, or they're all shifted in one direction, meaning cylinder 1 might be perfect and cylinder 4 is going to be offset like 30 thou, 40 thou, something like that, a visual amount. So correcting the core shift is huge, and that always translates into the short side radius too. You'll see if you put your finger in all the ports that, like I said, one cylinder, like usually cylinder 1 or cylinder 4, will end up being very good, and then the opposite side of it, it will have an edge in there where the factory valve job cutter went in there and cut a bunch away, and there's a huge lip in there from the core shift causing just from moving the material over, and then they had to remove it. The core shift's a big thing in the 4Gs. I've actually had some people bring me cores for an all-out race head that I just reject because the core shift's so bad. I think even if you could correct it in the port, but the material gets so thin that you're worried about going in the water at that point.
Yeah. Yeah, and it's another area where there's a lot of moving parts in there that sort of can affect what you can achieve in the finished result, correct?
Yeah, no doubt. Especially like core shift is huge for like chamber volume stuff and working on the chamber side of the valve and how you're going to shape that, how you want to shape that. And if a lot of times it's not even feasible if you have it shifted in the wrong direction. Like I used to have a couple of cutters I would use that I would cut I would call it unshrouding the valve, but I would cut the chamber to like where I'd put the head on a block and I'd scribe where the cylinder opening was. And then I would cut to that diameter with the unshrouding tool. There'd be times where one of them, it wouldn't even touch. It wouldn't remove any material. And on the other one, it was removing so much material, I had to cut it slower just because the core shift was so bad. So then you get all your machine work done, and then you've got to CC all the chambers and then massage them all to be the same, volume. So the compression ratio is as close as you can get it. It just, yeah.
And this is a perfect example of why tuning a stock engine where that core shift hasn't been corrected can be tricky when we're starting to push the limits. And when you start putting sensors on an engine like individual cylinder lambda sensors, and you start seeing the disparity in air fuel ratios between four cylinders at sort of 40 or 50 psi of boost, and people ask, well, how is that possible? Or everything that you've just mentioned is why we see those sorts of disparities. And obviously the harder we're pushing the engine, the more likely those disparities are to actually end up causing us some issues. So that's the difference with a properly prepared race engine. Everything has been corrected, or at least as well as possible. So we should get rid of those inconsistencies.
Yeah, what's an interesting thing about that is I've had a few people like that have individual EGTs, not necessarily individual Lambda, but individual EGTs, and they'll throw a tune-up in the car with, no fuel trims on each cylinder, no timing trims on each cylinder, and the EGTs will all be within 50 degrees of each other. You don't get that unless each cylinder is as close to efficient as you can make it, right? I mean, there's variances in the EGTs, obviously, that you have to kind of keep in mind there, but...
Yeah. Okay, and another element that I hear is really critical to the performance of a cylinder head is the valve seat, and some people say that's really the key secret in getting flow through a head. And again, the sort of multi-angle valve seat jobs and radius valve seats and all sorts of different techniques, and I guess everyone's got their own kind of favorite option. But what can you tell us about how critical that element is, and what's your sort of recommendation there?
Yeah, I would agree that that's the most critical part of the cylinder head. I mean, once you get having the best short side in the world for the head you have can all go to junk if the valve job itself is not up to par, right? So there's a lot of, it's very application specific. In intake to exhaust side, there's very different ways on how you treat those as well. For example, you mentioned a radius cutter. You would never put a radius cover on the intake seat. Another back to, it looks really good on a flow bench. But the fuel doesn't stay atomized, so typically they don't make as much horsepower. Now on the exhaust side, you can run a radius kind of deal if you'd like. The other thing to keep in mind there too is like seat width. On the exhaust side, we're going to run a wider seat to remove more heat out of the valve. right? So the exhaust valve obviously gets very hot. Then on the intake side's more based on flow. You're trying to also remove heat out of it, but it's not as crucial as the exhaust valve. And yeah, you just shape the valve job stuff can be tricky because it's going to vary depending on cylinder head and application. For example, I just did a R5P7 cylinder head. I don't know if you're familiar with what that engine is.
No, I'm not.
It's like a mid 2000s Chrysler NASCAR engine.
Okay.
Right. So it's a 2-valve. It had I can't remember the valve size. I think it was like a 180 diameter intake valve, right? But it had a 55-degree seat on it rather than like what a traditional stuff is, a 45-degree seat, right? And that's just because it spends so much time at super high lift durations. And we've thought about putting a 55-degree seat in a 4G head, but there's a lot of things to keep in mind there too. The seat tends to wear faster, it fatigues faster, and it's always advantageous at higher lift areas and not really in the meat of the area we run a 4G, right? Because our max lift isn't that high. So
yeah.
But yeah, definitely valve jobs are very crucial. It's like you said that you'd read, and one of the most crucial things of the cylinder head. I 100% agree with that.
This probably also comes back to an element of our valve diameter. And I mean, a lot of companies like Fourier or Supertech are producing off-the-shelf 1mm oversized valves for a lot of the popular import engines like the 4G63. And I think a lot of people are just sort of ticking the box and selecting those valves because, again, I mean, it comes down to the bigger is always better, right? Yeah. Is it an element of, and from your experience, I guess my question is it a valuable addition? What sort of percentage gains do you think we're likely to see by going to a 1mm oversized valve, keeping all other aspects the same? And, is 1mm the golden number, or given a different valve seat that would accommodate it, is bigger than 1mm even better for a high RPM, high boost application?
So I've played with this quite a bit on a couple 4Gs. We've gone from a stock intake valve, stock exhaust valve, to a mill over exhaust valve, a stock intake valve diameter, mill over on both. We've played with that quite a bit. What the crucial thing to me is, if you're going to put a mill over valve in it, the throat ratio to the valve size is a very crucial thing that often gets overlooked. If you put a mill over valve in it, you need to cut the throat to be the right percentage as the valve diameter itself. And a lot of times I'll choose the valve size I'm going to based on what the cylinder head comes in with, right? If it's outside of what I want for a valve ratio, say if the throat's already too big, then going to a mill over obviously makes sense, or whatever size over, right? You just calculate your percentage and go from there. Honestly, what I've learned in a lot of the experimenting with the 4G stuff, and back to something you said earlier about the casting flash thing, is like, I'm going to do it whether it makes sense or not, is on the cylinder head stuff. I've had guys hurt a head at the track and literally put a stock head in the car with the right spring, swap the spring overs, but an unported head with just a valve job, and gone within 3 mile an hour of each other. And that's on a car that's going 160 mile an hour. I think the big thing to take away from that is the turbocharger in that environment is our primary air pump. The turbine wheel is always the restriction. Regardless, you do the head as best you can to make as much use of that airflow availability as you can. But at the end of the day, the turbocharger's the main air pump there. So.
Yeah, and I think what it comes down to there as well is of course your budget and what you're actually trying to achieve. Obviously, if you want to go as fast as possible and make the maximum amount of power for a particular setup, then have at it. Go for gold, and the head is going to become a reasonably important element of it. But yeah, if you're a little bit more budget limited, as you say, the turbocharger really is probably the key element over and above the actual head porting. That's sort of my take on it as well. Now, another modification that we see made quite commonly for high boost drag engines is what's referred to as dry decking of the cylinder head, where the water ports between the head and the block are welded up. Can you start by giving us sort of a take on why is that something we'd want to do?
So we do that when we're going to fill the block. We don't want any coolant in the block. And a lot of times you could run, in theory, people do this. You could seal the deck of the block up and run water through the block and then externally route it through the head. A lot of that would be, in that particular situation, would be to just avoid any kind of connecting rod failure on top of a head gasket failure. So a lot of times you'll lose a head gasket, it'll take a big gulp of water in, and then it'll just break the connecting rod and you're out of block and all kinds of stuff that could have been avoided if you dry decked it. In the 4G world specifically, we fill those blocks because we start deforming them, over 1,100, 1,200 horsepower. They get to the point to where I haven't had one break, but it's just a concern and it's not worth the risk. So we'll just fill them with cement and then we dry deck the head, obviously, to coincide with that.
So just to kind of paraphrase what you're saying there, instead of running normal water coolant in the water jacket in the block, you're actually filling that to the very deck surface of the block with a grout or a cement type product. Now that's going to add rigidity to the block as well. I'm just interested, have you done any back-to-back, sort of coming back to our previous conversation about bore distortion, have you done any back-to-back testing to see if that actually stiffens the block and improves ring seal in and of itself?
But not in the scenario you're suggesting, not with a factory block that we've ran and then filled it and checked the ring seal after. I had a customer go from a filled factory block that I honed and prepped to a billet block that I honed and prepped on. The reason that's important is the cylinder wall finish was the same as far as ring seal goes, right? So that particular setup picked up 100 wheel with no other changes. And it was just a ring seal thing, yeah. We got to the point with the factory block. Now, it wasn't a strength issue. They were surviving. I mean, we went like 720s, 730s, 180, 190 mile an hour on an iron-filled iron block. But what they were distorting to the point when you fill them, you put all the freeze plugs in them, right? We were distorting those blocks to the point where the freeze plugs were falling out, even with them filled, right? So when you get to that point that the outside of the block is distorting so far, the freeze plugs are losing their press. We knew that
some flexes occurring in there.
Yeah, there's a lot of stuff going on, so that was the move to the billet block was worth quite a bit of power production. Not like, again, we didn't ever break a factory block, but from that point of view, the ring seal was significantly better just from the rigidity.
Yeah, I mean, I think that really is a nice graphical example of how important that ring seal is. And I think it also comes back to something I say a lot is, when you're looking at components like an engine block or a crankshaft and they're sitting there on the workbench, well, they look really rigid, but when you've got that cylinder pressure occurring and you're spinning the thing to maybe 10, 11,000 RPM with 60, 80, 100 PSI of boost pressure, it's a very different deal, and these components are going to be moving and flexing much more than a lot of people would consider. So, yeah, I mean, the billet blocks definitely have become a godsend, I think, for those people who really are pushing the limits, and not just in terms of its reliability plus the potential to make that additional power for aspects like the ring seal. Now, I'll just circle back to our dry decking because there's a couple more elements I wanted to talk about here. So we've talked about the sort of the block rigidity, but there's also a safety element here as well when we're drag racing, is that we definitely don't want to get any fluids out of the engine and potentially under the tyre. So that's another element there which the dry decking can help prevent. Probably worth mentioning that generally when you're going to the extent of solid filling a block like this, you don't obviously have the benefit of coolant there. So this is a technique that we normally see sort of associated with methanol powered drag engines. Does that sort of match your experience, what you're talking about here?
Yeah, 100%.
Okay. Now, one of the concerns that I've sort of got with the technique of welding up the alloy head is they're obviously introducing a huge amount of heat into that head. Does that have an element of affecting the hardness of the head? Because that's a big aspect of head integrity and sealing, is making sure that the deck surface of the head is hard. So yeah, how does that affect the head, or is it not really a consideration?
I've never seen it be a consideration. I would suggest, though, that the only area that's going to be affected by welding the head is the heat-affected zone around the weld. It's not going to actually change the mass majority of the cylinder head because the head itself isn't going to get that hot. Like when I do them, I'll preheat them to like 280 degrees. and then I weld them. I haven't shot them with a gun afterwards to see how hot they actually get during the welding process. I'm sure it's at that 280 or maybe even more than that. But I haven't seen, I don't know what temperature you got to get to say like anneal or like actually change the material on a metallurgic scale. I don't know. But I've never seen any issues from that at all.
Okay, so yeah, not the concern I thought it was. Maybe it's also an element of the water jacket that you're welding up is far enough away from that sort of ring around the combustion chamber where it's actually going to be doing the sealing to the head gasket. I'm not too sure. Again, not something that I've personally done, but I just wanted to see if your experience sort of showed there were any issues there. I actually want to circle back a little further, and this is something I probably should have asked when we were talking about valve sealing. Now, it's common to use a torque plate for the block boring and honing, which we've already discussed, but an element that I've seen a few machinists use as well is a torque plate for the cylinder head, on the basis that when they're cutting the valve seats, if you do that with the head bare, that's all well and good, you're going to get a good ring seal, but then when you actually bolt the head down onto the block, particularly if you're using some of these larger diameter fasteners with high torque settings, the same thing kind of happens to the valve seats. They distort just like the bores do. What's your sort of take on that? Is that something that's a concern, or is it not really an issue for the 4G heads that you're building?
So I guess I would answer that with experiences. I don't think that that would be crucial, and the reason I say that is if you do a leak down test on, say, a cylinder head or an engine that I've built, right, and the leak down test comes back 5% or less pretty much all the time, I don't know that it's going to get better than that, right? Or how much better than that you're going to get. There might be something to that. I would have a hard time understanding how far the seat itself is actually going to deform, as typically it is an aluminum head and a very hard materialed seat, right? So I don't know how much the seat itself is actually going to distort being forced externally by the aluminum surrounding it. I'm sure that it does have an effect, but I would bet it's so minuscule that it doesn't even matter.
Yeah, fair enough. I mean, I think probably the takeaway there is every head is potentially going to be a little bit different, and
for sure,
maybe that again is one of those things where we're starting to look for that last sort of 0.5% or so that isn't really as critical when we're sort of just trying to get that low hanging fruit, so to speak. Now, again, just related to that valve seat, so I'm sorry we've sort of gone round in circles a bit here, but when you've cut those valve seats, well, this is, how should I put it, more of a controversial topic that we see raised a little bit is lapping of valves, and I think this is a technique that maybe was used to improve the valve sealing on older engines, and the at least the advice that I hear these days is that doing that to any extent is going to result in a valve that seats really nicely at room temperature, but essentially if you get aggressive with the lapping and you're using an aggressive lapping paste, you end up with a concave/convex sort of valve seat arrangement, which only seals when the valve's cold, and as soon as the thing gets up to operating temperature, your valve sealing sort of turns to custard. However, there are instances where a light lapping can give you a really good indication of what your valve sealing is like. So it's sort of conflicting information, I guess. What's your take on all of that? Can you give us your advice?
If you're lapping the valve for anything other than to see what the seat looks like, if you're trying to save a cylinder head by using lapping compound on it in a performance environment, you're doing it wrong. Don't do that. Sure. Okay. If you're doing it to the point where you're worried about material removal or deformation of the valve or the seat itself, you're way beyond what you should be doing with lapping compound. What I do with lapping compound is because how you set the tooling up for a specific valve diameter, you adjust the tooling to the diameter. I'll cut the seat and then I'll lap it just very lightly to see where the seat is laying on the valve, right? Yep. And then as far as it sealing after you lap them, so even after I cut them with a carbide insert, dead pilot, blah, 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 tooling side of stuff, I'll actually put bluing compound on them and I'll hand stone them just to pull a little bit of the fuzz off, or if there's any kind of little bit of chatter from the machine work or any of that kind of thing. And then I vacuum check them before I send them out the door. And even when I've seen some of those that would say not vacuum check as well as I'd wanted, after they run for 10 minutes, they seal up perfectly. So
Yeah, absolutely. All right, yeah, so I just wanted to clarify that. But yeah, lapping does have its place, but you're talking a very light lap just to see where exactly that valve seat is located, as opposed to actually trying to correct a valve that is not sealing.
correct.
Okay, let's move on. And I wanted to just get a little bit of sort of experience from you on, I know you're involved with Kigley Racing with a Ford G63, which had the benefit of in-cylinder pressure monitoring as well as in-runner pressure monitoring. And that's something I haven't had the benefit of working with so far. It's reasonably expensive even these days still to add in-cylinder pressure monitoring, but I can only assume there's a huge amount of information that can be gathered. So can you talk us through what you're able to learn on that project?
Yeah, so we learned initially it was just a cylinder pressure sensor. Now, this is all Kevin's experiment. Kevin's a very intelligent person. And it was 4 years ago or so now when we did this last. But the biggest thing we were looking for originally is he's got a MyVac intake cam on his 4G, and we were playing with in-cylinder pressure sensors to see where the cam timing wanted to be, so we could manipulate the cam timing and see how that was affecting the cylinder pressure when the valve opened. He had traced on there where the valve would open, so we could see how fast the cylinder was filling, and we could move the cam timing to see how that would affect it. Obviously, the other thing from just in-cylinder pressure is looking at your ignition timing, seeing where MBT is, watching the pressures at crank angle change as you go up in cylinder pressure. A lot of cool stuff to learn from just the overall tuning approach, right, on that side of stuff. Another interesting thing we learned with that was he went from a 10-to-1 to like an 8-to-1 setup on the same combination, and we saw that the combustion stability on the higher compression engine was much more sensitive. The lower compression stuff, because we had to add so much ignition advance that the spark was happening at such a lower cylinder pressure that the combustion cycles were more similar in basically in peak pressures.
Interesting.
Yeah, it was cool.
Can you share any information on that comparison between the 8-to-1 and 10-to-1 compression setup in terms of what that did for the ultimate power as well as the sort of shape of the power and torque curves?
We made, now I can't remember the details exactly, like what boost level we were at. I believe we were typically at 60 pounds, 55 pounds or so on the dyno. That was an automatic front wheel drive car. I believe at 60 pounds, we were in the 8 to 900 area at the tire through a converter. And we were seeing when we broke a piston is why we went to the lower compression setup. He had a set on the shelf, so he changed them and came back. We ended up adding, I believe, 4 degrees, and we made within 15 horsepower the same number from the 10-to-1 setup. Spool wasn't very affected. It was a very eye-opening experience. One of those things we always wanted to do it and never really had the chance, and the opportunity just showed up.
Yeah, absolutely. I mean, it isn't something that a lot of people will ever get to play around with, but I know there's so many debates about the ultimate compression ratio and, how much the compression ratio is going to affect the response versus, how sensitive it is to timing and knock and ultimately, of course, power. And I mean, again, just like I mentioned earlier, unfortunately, we don't tend to be in a situation where we can test one engine with multiple compression ratios and get that solid back-to-back data on exactly what that does, which makes it harder for people to really get a solid answer on what compression ratio should I run. Yeah,
I have, if you want me to go into that a little bit more, I get that question a lot because I build a lot of 4Gs, right? So people are commonly like, what are we going to put, 10.5-to-1 or 9-to-1, or what are we going to do for compression ratio? And you compare that to the V8 world, where in the last 5-8 years, the V8 turbo guys have been going 10, 11, 12-to-1 compression stuff. Now 12-to-1's a bit high, but a lot of guys will be in that 11-to-1 area. And the reason they do that is because they can build so much more torque on the converter, they can get to their RPM they want, spool the charger faster, it helps that kind of stuff. In that environment, the majority of the guys are maybe running 30, 40 pounds of boost, right? So all of a lot of their horsepower isn't coming from the turbocharger. We're in a 4G. So like V8 naturally aspirated, a 2-point compression ratio change might be worth 60, 70 horsepower, right?
Okay.
Well, in a naturally aspirated 4G, it might be worth 10. You know what I mean? It's such an insignificant change because the engine is just so anemic by itself that it's really just, you're relying on the turbocharger for everything.
Yeah, no, that makes a lot of sense. I mean, I think as well, unless you're running on a really good quality fuel, maybe E85, race gas, methanol, nudging that compression ratio up, the relatively modest gains that it's likely to give you versus the walking a tightrope, I guess, with your tune-up. Sometimes the juice there maybe just isn't worth the squeeze, particularly if it's just a street-driven car where you're going to be predominantly running on pump gas. Slightly more conservative compression ratio, probably not going to really give away much in the way of power, but it's going to be a much easier combination to tune.
100%.
All right. Let's move on from our 4G63. I think I've got a bunch of knowledge from you, so I'll thank you for that, and I'll tuck that away in the back of my mind for future reference. I wanted to move on to another car that you mentioned, which is your own Gen 1 Ford Coyote, which, as far as I'm aware, is still the fastest Gen 1 stock engine Coyote on the planet. Is that correct?
Yeah, currently it is. Yeah, we're going to better that soon here, hopefully. But yeah.
So what sort of ET mile an hour are we talking here?
So it's been 859 at 155. For reference, it's a 3,740 pound car with me in it.
So it's quite light.
yeah, and it's a stock long block, so stock camshafts, timing chains. Never had a cylinder head off of it. Still even got a stock oil pan on the darn thing. Honestly, it's been a 1.2460 foot with a stock oil pan still. So it's still got a stock harmonic balancer on it. It's kind of scary, actually.
All right. So what have you done externally to get this thing into the mid-8s?
Well, the last, it had a forced inductions S480 on it. So it was a Bill 80. It was the, traditional Borg Warner 96 T6 132 hot side on the thing. I built my own intake manifold out of basically a Chinese copy of a Holley. I cut it apart, put an intercooler in it. Really, I mean, that's basically it. The header is very significant in that it's unique. It's a 180-degree header. I'm sure you're familiar with what that means, but for everybody listening, it takes every other cylinder in the firing order to one collector and all the rest to another. So basically, I have 2 cylinders from one bank, go to one collector, 2 from the other. They're all paired differently. So the header primary tube length is like probably, 20 inches longer than it should be for the operating range, but it makes it sound very, very unique, which is what I was going for. Other than that,
it's an Aiden spool up with that technique as well, though.
In theory, yeah, but I don't know in practice. I haven't, it's
another one of those areas where you didn't get to back-to-back test this, correct?
Yeah, you'd have to just put a whole other turbo setup on it and see what the differences were. I'm not sure. I mean, like I said, the thing works. It works very well. It lacks a little bit. The power curve doesn't look quite like what I want, but I don't know if it's a valve spring issue or not. But it falls over pretty bad at like 7,300.
Okay.
But
actually, while you mention that, because this is something that I get asked a lot about as well, is valve springs for naturally aspirated engines that have had a turbocharger added to them, and the sort of question around this is we've got boost pressure now on the back of the intake valve. So how critical is considering a valve spring upgrade for that sort of scenario?
I would say in a turbocharged scenario, it's not as significant in a supercharged scenario because the residual pressure in the cylinder is greater in a turbocharged scenario because you also have back pressure on the back side of it. So the pressure differential across the valve is probably fairly similar to what a naturally aspirated engine would be. In a blown environment where you're making, 20 pounds of manifold pressure with no exhaust back pressure, the valve spring is going to be more crucial. You can typically calculate the pressure difference based on the valve area, right?
Sure. Yeah. Yeah, I think the part that people miss with the turbocharged application is that back pressure element, which you've just highlighted, which you don't have in the supercharger application. So sometimes the scenario is maybe not quite as scary as it seems on face value. Yeah,
I can't believe I'm still on a stock valve spring on that thing. I mean, I turn it 8,200, even though the power curve is all done by 73, just from the gearing options I have with the trains that's in it. It's, still 4 variable cams. So I'm monitoring the variable camshaft all the time to see when I'm going to run into a valve spring problem. I'm assuming that the cam's going to start not being in time where I'm commanding it. I'm going to see some sort of camshaft timing problem come up with that. And I haven't seen it yet. And it's, that's at 26 pounds, 8,000 RPM, and everything looks kosher still on a stock spring. And for reference, I think that stock spring is only like 65 pounds of seat pressure.
Wow.
Yeah.
It's a pretty light spring.
Yeah.
All right. So when you're dealing with this sort of stock long motor deal and you're kind of creeping up on trying to break a world record, how do you find the limit? Is this based on what other people have been doing on the platform, or is it sort of a send it on the dyno, keep your eyes closed and your fingers crossed and hope it makes it through and see where you're at?
No, my approach has been, I would say I work 75% of it, I creep up to it, right? So I've made probably, 250 passes in that thing at like a 930 power level, right? A lot. And now it's tuned very conservatively. It's got a decent fuel in it. The timing's safe. It's an air-to-water intercooler, so the intake temps are cold. So it's tuned on the safe side pretty much all the time. I've never turned the car up over 14 pounds on the dyno because I kind of feel like, what's the point? If I'm going to break it, I'm going to break it going for the record again, right? But I usually run the car in that 14, 15 pound area. It'll do 930s. And then when we're going to go break the record, I just throw the kitchen sink at it. There's no creeping up on it. Because as soon as I start creeping up on that increments, I'm just adding more stress, more laps to the thing that could potentially be unnecessary,
Yeah.
Now, that hasn't bit me yet, and it might one day. I might say, let's throw 28 pounds at it, and it makes it 100 feet. I don't know, but...
I mean, it's important to understand for those listening here because there's always horror stories about engine failures, and my take on this has always been if you're tuning your average built street engine that's at moderate power levels, that's not something that should fail if it's tuned properly because you're choosing the right parts to suit your power level. And for most popular engines, there's a pretty well-known recipe on what's going to do what. However, where things do get a little different is when you are pushing the boundary, going places where no one else has gone before. I mean, in that application you've got there, there'd be absolutely no disrespect from anyone if you suffered an engine failure because you're trying to do things that no one has done and potentially no one really knows exactly where the line is. So at some point it's possible that you're going to step over it and that's sort of just the price that you choose to pay to try and break a world record like that. However, I just wanted to step back to the tuning because you mentioned you've got a pretty conservative tune-up there. So this is a part that a lot of people overlook as well. There are things that can be done with the way we tune a stock engine that can help produce power levels that would be seemingly unheard of on that platform in terms of the way we ramp the boost in, maybe timing around peak torque. Is there anything you're sort of doing there to sort of dull down the combustion pressure in areas where it could potentially be damaging to the engine?
A couple things. I run the ignition timing is 4 degrees less than MBT all the time. It's pretty safe. The other thing that I do is I keep the thing away from peak torque, meaning that I have a converter in it that's loose enough to where it's always over where peak torque is, just to try to keep it out of those peak cylinder pressures for long stroke duration, right, at the lower RPMs. That's really the two things. I haven't gotten to the point where my approach has been, I'm going to kill it with boost. I'm going to leave the timing really safe. I'm going to turn the charger side of stuff up until I can't anymore, and then we'll put some timing in it if needed at that point. Just because then I can keep the combustion stuff safe. I know it's safe if I pull 4 or 5 degrees out of it from where it should be happy. Keep the air cooled. With that air-to-water cooler, I mean, we're seeing intake temps like 55, 60 degrees Fahrenheit, right? So
wow. Okay, that's pretty cold.
Yeah, I'm running into efficiency issues with the core size. It's a Garrett 1,000 horse core, and we're pushing way more through that now. So I'm kind of starting to see 100, 110s if I'm, 26 pounds or so for any duration. But it hasn't been an issue yet. So
okay. Let's talk a little bit about the engine management side of things, because really that is the key to everything you've just talked about. And obviously, if you don't have the tune-up dialed in, reliability is just one problem. The other aspect is you've got no chance of actually getting the times out of the car that it's capable of. Now, you started, from what I understand, on the factory ECU, and these late model Ford engine control modules are pretty complex. So what's your tuning strategy been on that platform? Tuning technique, I guess I should say.
Well, my tuning approach is pretty much the same as far as like total timing and target air fuels. That kind of stuff doesn't really change. Just how you're achieving it. The stock ECU is, I don't know. It is very complex. Actually, that bit me one time. I ran into an airflow calculation that basically there wasn't a value available to me in the software to change. It would read 86 pounds of air a minute, and it would read more than that, as in the mass air sensor would continue to change above the airflow level, but the ECU wouldn't calculate the airflow level. So I had to send the file to somebody to have them modify the code to remove that limit and then send me, the stock ECU stuff is just so complex. And it gets more and more complex when you realize there's a lot of things that it's doing that we don't even have access to.
What hardware, software application are you using for the actual tuning on that stock ECU?
I started with SCT, and then I moved to HP Tuners. I've been with the HP Tuners side of stuff ever since then.
Okay. Now, this is a good point where people often ask, when should we be going aftermarket standalone versus stock ECU? And you have made that decision to go with the Haltech ECU now, and that's what you're running in the car. What was it that drove you to that? Was that kind of coming up upon these limits where you couldn't really tune the car properly or tune the engine properly anymore, or was there another sort of driver behind that?
Honestly, it wasn't the engine side of it so much as it was there's a couple things. It was a stock trans car still. I hurt the trans twice, and after the second time, I was like, I'm going to put a Turbo 400 in it. I was having issues with a bump box that would stage the car consistently at different transmission temperatures that I knew I could implement with a Haltech that I couldn't do with the stock ECU or any just aftermarket bump box controllers. They don't take trans temp into consideration at all. Obviously, power management was a big thing. There wasn't like a good, consistent way to pull ignition timing out of it. I was doing boost control with a boost leash. So it's a CO2 boost controlled car, and I would just ramp power in that way. And having all of those systems work independently of each other just became monotonous. It just like I was always worried I was going to forget something because everything was in, I had the boost controller in the glove box, and I had the bump box, under the kick panel, and then you had an MSD 2-step to run the rev limiter for that stuff. And you were just constantly messing with different boxes all the time. It just got monotonous.
And I think the other thing is at some point, you get far enough away from the stock setup that the standalone makes sense. I mean, when you're running the stock transmission, at least as far as I'm aware, you're really going to be needing to stay with the stock engine control module because the communication between the trans control module and the engine control is really critical for the trans to do what it's doing. So was that a case of when you swapped to the new transmission that freed you up and gave you the ability to go aftermarket as well?
Oh, it definitely did. Yeah, there was no good way for me to run the 6R80. No, well, there's a US Shift, I think, makes a box that runs the 6R80. But again, trying to move away from multiple tuning devices in one vehicle, right? It kind of eliminated that. So yeah, that was a big part of it. Here's an interesting side note. That car was stock ECU 6R80, so I dynoed it with the 6R80 and the locked converter 6R. It made 850 to the tire on 14 pounds. When I swapped to the Turbo 400, I went back to the dyno on the stock ECU. It was worth 140 wheel, just the converter change. Going from locked to unlocked, from the locked 6R80 to the unlocked Turbo 400, which I thought was really, really interesting.
That's a huge change.
Yeah, but after that, we moved to the Haltech. Haltech's so it's so amazing what you can do. You can do anything you want with it. Just like the launch control timing mess I've got a timing table that's based on distance from target boost and distance from target RPM. So it's constantly changing ignition timing to reach my target values there. And it's just limitless what you can do. That thing runs the parachute on the car. It runs the shifter. I'm doing everything in one box. The fail-safe side of stuff is cool. I don't really utilize much of it though, because I'm always worried that I'm gonna have a sensor fail and I'm gonna I have to abort a pass for a failed sensor, and that would bug me. But
yeah. I mean, there's pros and cons, I guess, with that sort of element as well, isn't there?
for sure, yeah.
Okay, and it's definitely nice having a one place to basically control all of the elements of the car as well, as opposed to, as you mentioned, all of those multiple boxes that you kind of may end up forgetting about one element, and that's obviously not going to end too well. So yeah, makes a lot of sense there. Look, Tyler, I think we'll move towards wrapping this thing up, and I'm obviously interested for a start, sort of, where do you sort of see the potential for that stock motor going? How much further do you think you can go in terms of power, and where do you sort of see the ETM mile an hour sort of ending up with it?
I'm really not sure. I have an 830 in my head as my target currently. But I think we might be able to do better than that. That last pass I made, the record pass was I left on 24 pounds and I ramped it all the way down to 20 by the time I was in second gear to try to save the thing through the top end. And now that I have the stock engine record, I'm kind of like, well, we're just going to throw the kitchen sink at it. So the last pass attempt I had was 26 pounds in it the whole time. I think that would have trapped somewhere in the 165, 168 area, probably 820, 830 in real world conditions. But the data looked so good from that. Now, that was an aborted pass. It knocked the tire off right when the converter started to couple, probably about 130 foot out. And the data to that point looked so good. I was really surprised. I think we can push it harder than that 26 pounds and still be okay. Now, at some point there's going to be a problem, but everything on the valve train side of stuff still looked really stable as far as monitoring the cam timing and all of that kind of thing. So it's never pushed coolant. It doesn't push anything in a catch can. I think it might have more room in there than I think.
That's impressive. Just wait for a good track then, I guess.
Yeah, we're going to a rental April 3rd here, so a specific radial prep rental. We'll throw the kitchen sink at it again, and I put a different charger on it, which I'm excited but a little concerned with, because as we talked before about how drive pressure can affect effective valve springs, right? So I went from that 96 Ford Warner turbine wheel to Force Induction's 104 millimeter with their new turbine wheel technology. So I'm knowing that I'm going to have a significant amount less back pressure. I'm hoping that isn't going to lead to a valve spring problem, but I don't know that. We'll see.
I guess that's one way to find out.
Yeah.
All right, Tyler, given your vast amount of experience so far in the industry in just about every element of the industry, is there anything you've learned that you would give in terms of advice to a younger version of yourself to maybe fast track your progress and your experience?
Probably don't be afraid to move into different platforms. I was in the turbo 2300 Ford market for a long time, and that market's 15 people. When I moved into the Mitsubishi world and started to be pretty successful in that environment, I wish I'd have done it 5 years sooner. And the same thing with the Mustang world. I wish I'd have got rid of my DSM, 5 years before I did, and got into the Mustang stuff as soon as I could. But
I think there's always a sort of a reluctance to move away from your comfort zone, and I mean that goes with just about anything. So I couldn't agree more. I've been through that with my old shop, sort of sticking to the JDM market that we knew inside and out. And when we finally sort of embraced some of the USDM vehicles and engines, I wish I'd done it years ago. It was such a good market, and the learning curve generally is not as steep as most people sort of expect it to be, I don't think either.
I would agree, yeah. Until you start tuning the Ford ECUs, then it's like, oh, all right.
Yes, Ford definitely, I think they looked at how everyone else was doing it in the OE world and sort of went and had a big meeting at head office and decided that they were just going to do it the most complicated way that was the most different possible. And I mean, definitely for us in the aftermarket, trying to understand their mentality is challenging. And it's not a simple ECU to tune, that's for damn sure.
Yeah.
Last question for today, Tyler. If people want to follow you and see what you're up to, how are they best to do that?
Best to do it's probably our YouTube channel. I've been putting a lot of focus into that. It's just Force Engineering on YouTube. Other way is our Facebook page. So again, Force Engineering on Facebook there. Or me personally, follow me personally, Tyler Hassing. I put a bunch of stuff on there for about the car, more day-to-day stuff. The shop sees more bigger projects and bigger stuff, but my personal page gets a lot of the day-to-day stuff we're working on, as well as the YouTube channel. I tend to highlight the cooler stuff we're doing on there. So.
Perfect. All right. Well, we'll drop some links into the show notes for those as well, so people can find that nice and easily. But Tyler, it's been great chatting. You're a mine of information there, and it's been really interesting getting your perspective on all of those topics that we've talked about. Appreciate your time.
Yeah, for sure, man. Thanks for having me on.
All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.